Hello and welcome to Unit 2, Phases of Matter, Lecture A. Today we're going to talk about the three phases of matter that we have to learn and the changes from one phase to the other, so the phase changes. So solid, liquid, and gas. Solids are going to be solids are going to refer to things that have what we call a definite volume and a definite shape. The particles in a solid are tightly packed and arranged in a pattern. They're shaking and moving all of the time, but they're stuck in a pattern. And I kind of refer to that like when you are in class and you're stuck in your desk in a specific seat, and you can move around within your desk, but you're supposed to stay put. Liquids are going to have what we call an definite volume. So their volume doesn't change. You can move them from one container to the other and they're the same volume, but they have an indefinite shape. So their shape changes depending upon the container that you put them in. So you know if you have water in a glass, it takes the shape of the glass. If you pour that water onto the ground, it's going to take the shape of a puddle. It's going to spread itself out. The particles in a liquid are close together, but they are arranged randomly. And then gases, last but not least, is going to have an indefinite shape and size. So indefinite volume and shape. They're going to take whatever size and shape container you put them in. So you release a gas into a balloon, it's going to stretch the balloon out until the balloon can't stretch anymore. Take that size and shape. You release a gas in a classroom, it's going to keep spreading itself out through diffusion until it basically takes up the full size and shape of the classroom. Gas particles are farther apart and randomly arranged. This is important. The state's going to ask you to draw little diagrams. So if you had to draw a diagram of a solid, you're going to put your solid pieces close together and in a pattern. Usually we draw them touching, and they shake back and forth. Different kinds of solids will have different patterns to them. Ice, for instance, when water makes its solid pattern, it makes little hexagon shapes. That's why we get the shapes of our snowflakes. Liquids, you're going to try to draw particles that are close together, but you have to make the arrangement random. And a lot of times this is hard for humans to do, to make things random. We tend to like to put things in a pattern. So be careful that when you do it, they really truly come out random and that you're not making some other kind of pattern to it. They typically are touching each other, some little gaps and spaces. Gases have to be randomly arranged and far apart. And this is another one where it gets really easy to accidentally put them into a pattern. But on a test, what the state is looking for is that they ask you to draw two different phases, and I have to compare. Is your liquid more random than your solid? Are your gas particles farther apart than your liquid? So that's what they're looking for. When we change them from one to the other, we give those phase changes specific names. So the first one we're going to look at is when things melt or freeze. They're going to melt and freeze at the same temperature. So the melting point, which I abbreviate a lot of times as MP, and the freezing point, FP, are the same temperature. And this doesn't necessarily have to be warm or cold. It depends on the substance. Melting, freezing, sometimes called fusion. We talk about fused salts. And if you look on this graph right here, this flat spot is going to be our melting. As we're heating the substance, we're adding heat, so it's going to melt as we go from left to right. Heat's being added left to right. They have a little delta H fuse underneath here. That is for the heat of fusion. So take a second and grab your reference tables and go to the back side. Go to table T. And we're going to go all the way down to the bottom of table T. And we're going to zoom in a little bit here. And we're going to look at the equations for heat. So far, we used this equation, Q equals mc delta T, and that was used when the temperature changes. So if we're heating a substance and the temperature changes, we use this equation. On a phase change diagram, that's going to be the slanted parts of the graph. We have Q equals mH sub F. Q for heat, M for mass, H sub F, the heat of fusion. This is the equation we are going to use when something melts or freezes. When something's melting, it's absorbing that amount of heat. When something freezes, it's releasing that amount of heat, and it's going to be a flat spot on our graph. Then we have this last equation down here, which we didn't look at on our graph yet, but as long as we're on table T, we might as well take care of it. Q equals mH sub V. H sub V over here, Q still heat, M is still mass, H sub V is the heat of vaporization. So when you see vaporization, hopefully you think of gases. This is the one that we're going to use when something boils or condenses. It's going to absorb that amount of heat when it's boiling. It's going to release that amount of heat when it condenses. And that will be the other flat portion of our graph when we go back to our phase change diagram. So slanted parts on the graph, we use Q equals mc delta T because the temperature is changing. Flat portions of the graph, the temperature is not changing, so we can't use this equation. We know the amount of heat is changing, but if we plug in a 0 for the change in temperature, the equation will come out as 0 heat, and we know that's wrong. So we have to use a different equation. They came up with these constants. Every substance will have its own specific heat of fusion and heat of vaporization. So those are constants. The only one you're going to be responsible for is water. So let's take a look at water's heat of fusion and heat of vaporization. I want you to flip to the front of your reference table and find reference table B. So over here on reference table B, they have the physical constants for water, and there's 3 different ones listed here. So heat of fusion is going to be shorthanded H sub F. That's the amount of heat that it takes to melt 1 gram of solid water into liquid water, or the amount of heat that needs to be released to freeze 1 gram of liquid water into solid water. And it's 334 joules per gram. Next is heat of vaporization. They shorthand that H sub V. Heat of vaporization is the amount of heat that it needs to be absorbed to turn 1 gram of liquid water into 1 gram of gaseous water. It also is the amount of heat that needs to be released to turn 1 gram of water vapor into 1 gram of liquid water. And that's 2,260 joules per gram. So one of the things that I want you to notice here is the difference in the amount of energy. So I had said earlier that solids were like being in the classroom, and they're tightly packed particles, and there's pretty strong forces here holding them together into a pattern. But that in a liquid, they just break those patterns. So they're still pretty close together, but now they're going to be able to slide past each other. So they're not doing a whole lot of movement here other than breaking their patterns and being random. I kind of think of that as when the bell rings and you leave and you're out in the hallways. You're still pretty close together. There's other people in your way. You've got the slow ones and the fast ones, but you don't have tons of energy. Gases, on the other hand, remember, we're really far apart and moving rather quickly and independently of each other in all kinds of different directions. It takes a lot more energy to overcome the attractive forces keeping these particles close together in order to be very far apart. So if you look at these two values, you can see that per gram, it's going to take you a lot more energy to get water to boil than it is to get an ice cube to melt. Last on this chart is our C. So that was our specific heat, 4.18 joules per gram degree Kelvin. So 4.18 joules to change the temperature of 1 gram of the substance 1 degree Kelvin. Remember, heat of fusion, that's the melting freezing flat portion of your graph. Heat of vaporization is the boiling condensing flat portion of your graph. And the Q equals MC delta T with the specific heat are the slanted portions of your graph. So let's go back to our lecture notes. And again, look at this phase change diagram. So this is our heating curve. Across the heating curve, we are adding heat. If we are adding heat as we go from left to right, all of these phase changes as we go from left to right are going to be endothermic. They're endothermic because we're adding heat. It's absorbing heat as we go across our graph. Over here we have the temperature. Okay, and the temperature during these flat portions doesn't change. So a lot of times we think of melting an ice cube, the temperature must be going up. But the temperature is not going up, the temperature is staying the same. Where the temperature is called our melting point, and I'm just going to abbreviate that MP. The amount of energy required is the heat of fusion. The melting point is the temperature, and remember that's an arbitrary scale, and it's going to be different for each substance, and so will the amount of heat be different for each substance. They're constants. The next flat portion on our graph is going to be for boiling. Our definition of boiling in chemistry is going to be slightly different than what you're used to. You're kind of used to the idea in cooking where if it's boiling, you see all these big bubbles and there's steam coming off, and you have that rolling boil picture in your head. But in chemistry, the particles of the liquid, remember, aren't sitting still, they're moving around. And some of them have more energy than the others, and they'll bump up and they'll hit the surface and they'll escape and leave. If that's happening at a temperature lower than the substance's boiling point, it's a slow, random process, and it's called evaporation. There's a direct relationship between how hard those particles are hitting the surface, we call it the vapor pressure, and how hard the air is pushing down on the surface, that's the atmospheric pressure. So a direct relationship means if we increase one, we increase the other. So if we increase the temperature, we increase the vapor pressure. Boiling in chemistry is going to be when the vapor pressure equals the atmospheric pressure pushing down. So when we hit that point, notice that the temperature doesn't change anymore. That temperature is called the boiling point. And once we hit that boiling point, the temperature stays the same until it's all a vapor. So down here, we have a solid. Here we have a solid and a liquid as solid turns into a liquid. At this slanted section we have just liquid. At this next flat section we have a liquid and a gas as the liquid turns into a gas. And then at this point it's all a gas, only gas there at that phase of matter. If we look at the energy changes, at the slanted portions of the graph, the kinetic energy is increasing, and so is the potential energy. Energy is getting stored up. Those particles are moving faster. They're able to slam into each other more. They will have more energy. If you stop adding heat, they're still going to have more energy to be able to move around with, so the potential energy also increases. At the flat sections, the kinetic energy stays the same. Temperature stays the same. Remember, kinetic energy is average kinetic energy. So the only thing changing during a phase change is the potential energy is increasing. We're still adding heat, so the potential energy continues to increase. Next slanted section, both the kinetic energy and the potential energy are increasing. At the next phase change, here is our vaporization or boiling phase change. Again, only the potential energy is increasing, the temperature stays the same. And then once we hit a gas, both the kinetic energy and the potential energy both increase. One last phase change that you will be asked to know is sublimation. Sublimation is a special type of phase change. So their particles hit the surface very hard all of the time, and it's very easy for them to turn into a gas. These have such high vapor pressures that they will go straight to a gas without melting. So they're not going to turn into a liquid. There's two that you need to know. Carbon dioxide solid, also called dry ice, also written as CO2 solid, will change directly into a gas at room temperature. And iodine solid will also turn into a gas at room temperature. One of the common misconceptions is that iodine is a liquid, because you go to the doctor's office and they use iodine on your arm before they give you a shot. You used liquid iodine solution in biology to test for starches. But that is a solution. That is technically called iodine tincture. And a tincture is a solution made with alcohol for your solvent. And that's why it works as a great disinfectant. Both the alcohol and the iodine work as a disinfectant. That is your liquid. But pure iodine is a solid, and it sublimates. And it sublimates into this really pretty purple vapor. The opposite phase change for sublimation is called deposition. So if you have a gas turning into a solid, they call it deposition. Water can do this, but only at temperatures well below 0 degrees Celsius. So since it only happens at temperatures well below 0 degrees Celsius and not at room temperature, we don't typically say that water sublimates. But in your freezer, when you have an ice cube tray in there, if it sits in there too long and the ice cubes look like they've shrunk and they're smaller than the cubes in the ice cube tray, that's because that solid water has sublimed into water vapor in your freezer. And if you open up your carton of ice cream and there's all those ice crystals on it ruining your ice cream, that's because the water vapor that was in your freezer has deposited itself into ice crystals onto your ice cream. And there was no liquid phase involved there. But again, they're not going to say that it's sublimation or deposition normally because it's not happening at room temperature. So dry ice and iodine, you're going to memorize those two. Okay, and then of course, our equations on reference table T. Down here are table T equations. Let's take a look at those and try a problem. Okay, so again, Q equals MC delta T for when you have a temperature change. Q equals MH sub F for melting or freezing, absorbing when you melt, releasing when you freeze. And Q equals MH sub B for absorbing when you boil and releasing when you condense. So the question wants to know how much heat will it take to melt 120 grams of ice. So we have 120 grams and they're melting it. So that means we want the Q equals MH sub F equation. Heat is what they want, so that's our Q. The mass is 120 grams. And our H sub F, remember, again, is on table B, and it's 334 joules per gram. The grams will cancel. If we had left the units in, the grams would cancel, and we would have joules left. And then all we need is our calculator. And we have 120 times 334. And we have 40,080. And the units here are joules. Remember, the grams are going to cancel, and joules are all we're going to have left. Next question says, how much heat will it take to boil the same sample? So heat is again Q, and boiling it means we're going to use Q equals mH sub V. So Q equals mH sub V. Our mass is still 120, and our H sub V this time is 2,260. So we get our calculator. 120 times 2,260, and we have 271,200. And again, the units here are joules because the grams cancel. So just like I was saying earlier, it takes a lot more heat, a lot more energy to get these particles to overcome the force of attraction between the water particles to get them to spread out enough to be a gas. This is why steam, which is even hotter than your boiling water, has so much energy and so much heat and can do such damage when you get burned. So you have to be really, really careful with steam. Okay, last thing here on our lecture notes before we look at some examples of boiling and freezing is our cooling curve. So it's just the opposite of the heating curve. We're going down. You could always just read your heating curve backwards, but sometimes they'll draw you a cooling curve instead. So here we're starting with a gas. We have a gas turning into a liquid. That's called condensation, or we say it is condensing. So this would be our condensation point. Same temperature as your boiling point if you have the same substance. This section would be a liquid only. Here we have a liquid turning into a solid called freezing, called solidification, sometimes called crystallization. So lots of different words for that one. And then down here we have nothing but solid. Just like on our heating curve, wherever it's slanted, the kinetic energy is changing, but in this case the kinetic energy is decreasing and the potential energy is decreasing. On our phase changes, the temperature stays the same, but the particles are now slowing. They're not slowing down. Their motion is changing in a way that takes less energy. So from a gas to a liquid, they're getting closer together. From a liquid to a solid, they're putting themselves into a pattern. So here, slanted going down, the kinetic energy is going down and the potential energy. Here, as our particles arrange themselves into a pattern and it takes less energy to sit there, the potential energy decreases, and again, kinetic energy decreasing, potential energy decreasing. Remember that a gas can be much hotter than its boiling point, and a solid can be much colder than its melting point. All of these phase changes are going to be exothermic. As we go from a gas to a liquid, or a liquid to a solid, or even from a gas to a solid in deposition, we have to release energy as those particles change their arrangements, and so they are all exothermic. Remember, try to not associate temperatures with this in your head. It's not necessarily hot or cold because the temperature stays the same. The temperature stays the same. It's just the amount of heat that they contain that decreases, and they're not always the same thing. All right, let's take a look at some examples of phase changes. So we have over here solid ice turning into liquid water, and we know that that happens at 0 degrees Celsius. So this is going to be melting. So that water is at its melting point at 0 degrees Celsius, and it's slowly turning into this puddle. Over here, though, we have iron, and iron melts at about 1536 degrees Celsius. Now, the exact melting point will depend on what other mixtures are in here and which form of iron, But that's an approximate melting point there. One of the things that happens is, melting and freezing are going to happen at the same temperature. So where I can say water's melting point is 0 degrees Celsius, I can also say its freezing point is 0 degrees Celsius. Iron's melting point, 1500 degrees Celsius, is freezing point, 1500 degrees Celsius. Because we use the term freeze in English to kind of mean it's cold, because we're usually referring to it like water, over here, when I say things are freezing, that magma is freezing into rock. It's going from a liquid to a solid. Also called solidification sometimes. Solidification, probably a better term to use for the magma because it doesn't imply cold in our language. Sometimes called crystallization, and that's what these compounds are doing, forming crystals over here. But they could also be said to be freezing. This happens, magma has a melting freezing range between 700 and 1300 degrees Celsius. Just depends on the magma. That also not cold. So you need to remember that freezing in chemistry does not mean cold like it does in English. It means the phase change of going from a liquid to a solid. Sometimes we use the term crystallization because many compounds form beautiful crystals, and the crystals can actually be used to help identify them. So as the liquid cools and it forms these different structures and different shapes, they might call it crystallization. Specifically used for things that they call true solids, form these beautiful little crystal patterns. All right, we have the same temperature issue with boiling. So here we have boiling, condensing. So these are two examples of boiling. So here I have water boiling. So the liquid's turning into a gas. But here I have liquid nitrogen. This liquid is also turning into a gas. So you see the gas vapor all pouring out the sides. Water boils at 100 degrees Celsius. Liquid nitrogen boils at negative 196 degrees Celsius. So room temperature, as soon as that liquid hits the air and it's not under pressure anymore, it begins to boil because room temperature is much higher than liquid nitrogen's boiling point. Again, a boiling point that we would consider hot because it would damage and hurt our skin. This boiling point we would consider extremely cold because it would also damage and hurt our skin. But we don't necessarily think of things boiling at such cold temperatures. So you have to make sure that you dissociate your conceptions of boiling or freezing with any specific kind of temperature. In this diagram, I like this one because they're showing you the distillation process, and that's going to be using phase changes to produce a product. We're going to separate a mixture. So here we have fire. The fire is adding heat to this water to boil it. So that's going to be an endothermic change. Endothermic change. So we're adding heat to the water, and this liquid water is turning into a gas. So liquid to a gas, endothermic. That steam separates out other liquid compounds from this plant material. So pretend these are rose petals or leaves, some kind of plant they want to make a perfume out of. And up here we have just gas, and that gas is going to go into this condensing chamber. So condensing, turning a gas back into a liquid. We have this cold water here. This steam in this pipe is going to release its heat to the cold water. If the steam is releasing its heat to the cold water, this phase change from a gas to a liquid is exothermic. And then we have just pure liquid dripping down here to where it's going to separate out. The oils that they used for really good perfumes on the top, and our water that just now smells like the good oils down here at the bottom for cheaper perfumes and colognes. But distillation is going to be the process for separating a mixture using boiling points. So it's going to be using that liquid to gas and gas back to liquid phase changes. Down here are some examples of sublimation, so you can see exactly what we're talking about. Solid CO2 just looks like a regular ice cube, but it gives off this vapor. So there's your CO2 gas. No puddle of water, no melting, extremely cold. And here is our solid iodine, and I told you iodine was a solid, little crystals. In the chamber here, we have our iodine gas. It's really a pretty purple vapor. When we do a lab where we separate out iodine, you'll see a lot more of it in there than this picture is showing you. But it's a purple gas, and then here it's redepositing itself. So deposition, it's turning back into solid iodine crystals on the dish. And that means they probably have some kind of ice up here in the dish to cool that off so that it can go back to a solid. From a solid to a gas, endothermic, it's going to be absorbing heat to do that. There's just enough heat in the room temperature to turn this solid into a gas. Same thing with the iodine. There's enough heat in this room to turn this solid into a gas. That should wrap up part 1 of Unit 2 phases. Next lecture, we'll be talking specifically about gases.